Assalamu alaikum viewers. In this lecture, we will discuss Crystal Field Stabilization Energy or CFSE for octahedral geometry. If you like this video, please like, share and subscribe this channel. In the previous lecture, we have discussed crystal field separating for various geometries including tetrahedral, octahedral, tetragonal and square planar geometries. So if you want to know all about this lecture, then please go to my channel and in the playlist section please select coordination chemistry and you will find all the lectures related to coordination chemistry including this lecture. In current lecture we will discuss about crystal field stabilization energy. So you can also say that we have learned the crystal field splitting only because of to understand how we will calculate crystal field stabilization energy. So crystal field stabilization energy is directly proportional to the stability of the coordination complex. Like if the crystal field stabilization energy value is greater, then the complex will be more stable. When we talk about its stability, then we mean thermodynamic stability of the coordination complex. Like the complex will be break down by giving some extra energy in the form of heat. So if the crystal field stabilization energy is greater, then that coordination complex will have more stability. But if CFSE value is less, then that complex will be less stable. So one thing must remember that it is not an ordinary energy but it is stabilization energy. So students should not confuse it with the concept of energy, that if energy is greater then stability will be less. This is not the energy, this is actually the stabilization energy. So greater will be its value, greater will be the stability of the complex. Actually, in some books, the calculation has been written in other way, but I am following the book of coordination chemistry by Johnson and Basalo. So it is the most authentic book as far as coordination chemistry is concerned. So we will calculate CFSE or crystal field stabilization energy values according to that book. In this particular lecture, we will calculate CFSE values for only octahedral geometry. So in this picture, if you see here, this is the crystal field separating for octahedral geometry in which the dx square, y square and dz square orbitals go high in energy and dxy, dyz and dxc orbitals go low in energy. So it is for D10 system. D10 means the elements of the periodic table which have only one electron in d orbital. So like scandium and yttrium in +2 form, then these elements will be called as D10 system. So the one electron is placed here, it will be placed here, and when the geometry is octahedral, so it will be placed here. Now here dxy, dyz and dxc can be exchanged, it is not fixed. Similarly dx square, y square and dz square is not fixed. So we can choose to place electron in one of these orbitals. So we have currently placed it in dxy system. So how we will calculate its energy? So if you see here, this is D10 system and this is one electron, and as the del O value for all these three orbitals is 0.4, so we will multiply this one by 0.4, so the answer is 0.4 del O. So the CFSE value for D10 system including elements such as titanium, the elements such as yttrium and scandium, for these elements whenever they are in their +2 form, the 0.4 del O will be their crystal field stabilization energy value. When there is one electron, so when in crystal field separating for octahedral geometry, we will place here in the low orbitals because the orbitals of low energy will be filled first as compared to the orbitals of high energy. So this single electron will go into lowest energy level. So in order to calculate CFSE value for D2 system, meaning which have elements which have uh, two electrons in their d orbital, such as titanium plus 2 form, zirconium plus 2 form, and hafnium plus 2 form. So all these elements constitute the d2 system. So these electrons will be placed here, then here, and again the second electron will also go in the lowest possible energy level. So now if we calculate the energy, there are two electrons, and the value for each dxy and dyz, the CFSE value is zero point 0.4. So 2 multiplied by zero point 0.4. So total CFSE value for D2 system octahedral geometry is zero point 0.8 del O. Now it means D1 system was having value of zero point 0.4, whereas D2 system having value of zero point 0.8. So it means D2 system is more stable as compared to the D1 system as far as stability of coordination complexes are concerned. For D3 system, another electron will be added here. These electrons will be placed here, and the third electron will also go to the lowest energy level possible rather than it goes to high energy level. So now D3 system involves elements such as vanadium, niobium, and tantalum in their plus 2 oxidation state. So now there are 3 electrons, so 3 multiplied by zero point 0.4. So overall D3 system crystal field stabilization energy value is 1.2 del O, which is again greater than del 1 D1 and D2 system. So it means D3 system complexes are more stable as compared to the D2 and D1 systems. So in D4 system, another electron is added, and now there are 4 electrons, and the 4 electrons will be go in the lowest possible energy levels because there is space available in the lowest possible energy levels. So D4 system is slightly having different calculations as compared to D1, D2 and D3 system. The reason is that here when we talk about D4 system, or the element which have 4 electrons in their d orbital, these elements include chromium, molybdenum and tungsten in their plus 2 oxidation state. So here there are two cases. One case is for strong field ligands and other case is for weak field ligands. Now in case of strong field ligands such as carbonyl and cyanide, this gap is so much greater than there is no possibility of the fourth electron to jump into dx square, y square or dz square. So all the electrons will be paired up here in dxy, dyz and dxc. So as there are two cases, so first of all we will deal with strong field ligand case in which the ligands such as carbonyl and cyanide are present. So in this case this gap is greater. All electrons will be placed here in the dxy, dyz and dxz orbitals. So D4 system 4 electrons, and each value for these orbitals is 0.4 del O. So 4 multiplied by 0.4 is equal to 1.6 del O. So crystal field stabilization energy for D4 system for chromium, molybdenum and tungsten, and in case of strong field ligands the value of CFSE is calculated to be 1.6 del O. In case of D4 system for weak field ligands such as halogens, water, etc., the fourth electron will be placed in dx square, y square and dz square, because in case of weak field ligands this gap is not so much greater. So the orbitals will be first filled singly, as these three orbitals are filled singularly. So the fourth electron will be placed in the higher orbital because there is less gap due to the weak field ligand. So the calculation will be slightly different. So first of all we will calculate crystal field stabilization energy for electrons that have been gone into dxy, dyz and dxc. So 3 multiplied by 0.4 is equal to 1.2 del O. Now the fourth electron that has gone into the higher energy level dx square, y square. So the value for these orbitals is 0.6 del O or 0.6 crystal field splitting parameter for octahedral geometry. So the value for this electron will be 0.6. Now question is whether we will add this value in this value or subtract it. So the answer is that we will subtract this value from the lowest value of 0.4 del O. The reason is that here when electrons have been gone into this dx square y dyz and dxe, then they have gone into low in energy. So if you see here, this is the energy parameter. If we go high in energy, then it means we are going there is loss in stability. But if we go downward in energy, then we are gaining the stability. So this is the simple ordinary energy, and this is inversely proportional to the stability, whereas this CFSE is directly proportional to the stability. So in D4 system, the stability gained by moving down in the energy is 3 multiplied by 0.4 is equal to 1.2 del O, whereas energy of this 4 system is greater. So this causes destability in overall coordination complex. So what we will do, we will calculate overall stability, and then we will minus this instability in order to calculate the overall crystal field stabilization energy of the complex. So that is why 3 multiplied by 0.4 is equal to 1.2. So this is the net stability gained by these 3 electrons, and this is the actually instability by the movement of this electron in the dx square, y square or dz square. So we will calculate its value, which is 1 multiplied by 0.6. 0.6 has been come because the value for these 2 orbitals is 0.6 del O, as the value of these 3 orbitals is 0.4 del O. So 1 multiplied by 0.6 is 0.6, but we will place a minus here because this is loss in stability. So in order to calculate overall stability, we will add gain in stability and subtract the loss in stability in order to gain the net stability, which is 0.6 del O in this case. So if you compare the value now, as the 4th electron has gone high in energy, so that is why the overall CFSE value for D4 system is less as compared to the previous calculations of D2 and D3. So in this way, we calculate the second case of D4 system in which the ligand is weak field such as halogens and water, etc. So in this case, the value will be 0.6 del O, whereas in case of strong field ligands, the value was 1.6 del O for the same D4 system. The question may arise here that why the 4th electron has gone into the dx square, y square and dz square orbitals or high energy orbitals. The reason is that when there is a weak field ligand, then this gap is small. So the electrons are following the Hund's rule that if the space is available, then electrons prefer to place in the separate orbitals with the same spin rather than to place them in the same orbital with opposite spin. So here, if the gap is less, so electron will be preferred to place in the different orbital with the same spin. In case of strong field ligands, the gap is so much greater that the Hund's rule is not obeyed here, because the 4th electron cannot go in the normal energy environment in dx square, y square and dz square. Rather, it will be placed by force in the lowest possible energy levels. So the placement of electrons in the orbitals is just like the hostel rooms and students. Like if there are 5 orbitals and there are 4 electrons, it is just equal to the analogy of 4 hostel rooms with 5 hostel rooms with 4 students. So all the students will prefer to place in the separate rooms rather than to pair up. So electrons will also do just like this. They prefer to place in the separate orbitals, but here the reason is that by force the electron has been paired up because it cannot go into the high energy level because this gap is too much greater for strong field ligands. But here the electron can jump and can go into high energy level and can place separately because this gap is less due to the presence of weak field ligands. Just like D4 system, the D5 system will also have two cases. First case will be for strong field ligands such as carbonyl cyanide, and if you see here that there are 5 electrons and these 5 electrons will be placed here. So again, due to the strong field ligand, this gap is so much greater that all these 5 electrons are paired up here. So the CFSE value for D5 system for strong field ligand will be 5 multiplied by 0.4, which will be equal to 2.0 del O. D5 system includes elements such as manganese, technetium and rhenium in their +2 form. So this is the CFSE calculation for weak field ligands such as water, halogens, etc. So in this case this gap is less, so 3 electrons will be placed here and the 2 electrons will jump into higher dx square, y square and dz square orbitals. So their CFSE value is calculated as, first of all, for these 3 electrons the value will be 3 multiplied by 0.4 is equal to 1.2 del O, whereas value for these 2 electrons will be 2 multiplied by 0.6 is equal to 1.2 del O. So the gain stability here will be minus from the loss in stability by placing these electrons in the high energy levels. So this value has been deducted or minus by this value, and overall if we see here that del O is 0. So it means for D5 system, like for elements such as manganese, technetium and rhenium in their +2 oxidation state, and for weak field ligands, there is no net gain in stability as CFSE value is 0. It means these complexes will be very least stable. So first of all, they will not formed, and if somehow they are once they are combined together, then they will be separated, like metal and ligands will be separated because of very less stability. If you see here, D5 system is actually the system having D5 electrons. D5 electrons means that half-filled orbital. So half-filled orbitals are all elements are already stable, so they will not form any complex, as we all know that the purpose of this complex formation is to gain stability. So as D5 system is half filled, so these elements are already stable, so they don't want to form any complex to gain further stability because they are already in stable state. So that is why the CFSE value for D5 system for weak field ligands is 0. So here we will calculate CFSE for D6 system. Again, just like D5 and D4 system, D6 system will have two cases. One case is for strong field and other is for weak field. So first of all, we will see for strong field ligands. So here we have placed 6 electrons, here we have placed, and all the 6 electrons will go into the lowest possible energy levels, and they will not go into the high energy level due to the greater gap of this due to the strong field ligands. So 6 multiplied by 0.4 is equal to 2.4 del O, which is the crystal field stabilization energy for the systems such as iron, ruthenium and osmium in their +2 oxidation state. In case of D6 system for weak field ligand, the 4 electrons will be placed here and 2 electrons will be placed here. So how we can arrange this just like this? First of all, as this gap is too much less, so electrons first will be placed singularly, like 3 electrons here and 2 electrons here. Now the 6th electron will go again downward and will be placed here. So it means first case scenario, the electrons will be placed singularly and then the sixth electron will be placed in the lowest possible energy level in paired form by force, because now there is no possibility the sixth electron must have to be paired in some orbital with some other electron with opposite spin. So here first of all we will calculate the CFSE value for these orbitals and then these orbitals, then we will deduct this value from this value in order to gain the noble overall stability. So again, for these 4 electrons the value will be 4 multiplied by 0.4 is equal to 1.6 dal O, and the value for these 2 electrons will be 2 multiplied by 0.6 is equal to 1.2 dal O. For net stability, the answer is 1.6 minus 1.2 is equal to 0.4 dal O, which is the CFSE value for D6 system involving elements such as iron, ruthenium and osmium in their +2 oxidation state with weak field ligands such as water and halogens, etc. Just like D6 system, D7 system will also consist of two cases like that of strong field ligand and weak field ligand. So if we see here that there are 7 electrons in the d orbital for the elements such as cobalt, rhodium and iridium, these 7 electrons will be placed here. So in case of strong field ligand, the lower orbitals will be filled first, and the lowest orbitals are completely filled, whereas one extra electron will be going towards dx square, y square and dz square. Although this gap is greater as the presence of strong field ligands increase this gap, but now there is no possibility as the lowest orbitals are already filled. Now we must place the extra electron and there is no other option, so the extra electron will go into dx square, y square or dz square. So the energy is calculated as there are 6 electrons, so 6 multiplied by 0.4 is equal to 2.4 dal O, and for this extra electron the value is like 1 multiplied by 0.6 is equal to 0.6. So we will calculate total crystal field stabilization energy value for D7 system in case of strong field ligands, which is calculated to be 1.8 dal O. Now in case of weak field ligands, this gap is less and this gap is less, then electrons will jump into these energy levels also. So just like D6 system, the electrons will be first filled singularly and then extra electrons will be paired up. Like we first fill the 5 electrons just like this, and then 6 electrons will be paired here and 7 electron will be paired here. So this is the situation of electron placement in dxy, dyz and dxc and dx square, y square and dz square in the presence of D7 system in the presence of weak field ligands. Now the energy is calculated as there are 5 electrons here, so 5 multiplied by 0.4 is equal to 2.0 dal O, whereas for these 2 electrons which are placed in dx square, y square and dz square, the value is 2 multiplied by 0.6 is equal to 1.2. So overall CFSE value for D7 system including elements such as cobalt, rhodium, iridium in the presence of weak field ligands such as water, halogens, etc., the overall CFSE value is 0.8 dal O. System D8 system will also have only one case, like this is the only crystal field splitting pattern and placement of electrons. And D8 system include elements such as nickel, palladium and platinum in their +2 oxidation state. So here are 8 electrons, so 6 electrons will be placed here and the 2 electrons will be placed here because the lowest energy levels are filled, so they must have jump into these high energy orbitals whether the ligands are strong or weak field ligands. So the 6 electrons placed here, so 6 multiplied by 0.4 is equal to 2.4 dal O, and for these 2 electrons the value is 2 multiplied by 0.6 is equal to 1.2 dal O. So overall the CFSE value for this complex like D8 system of nickel, palladium and platinum for both strong field and weak field ligands, there is only one value and that is 1.2 2 del O, which is the CFSE value for octahedral geometry of these system elements. So this is the diagram for D9 system involving elements such as copper, silver and gold in their +2 form. So there are 9 electrons. These 9 electrons are placed here. So 6 electrons are placed here and 3 electrons are placed here. So the CFSE value for this system is calculated as 6 multiplied by 0.4 is equal to 2.4, which is value for these electrons, and for these electrons the value will be multiplied by 0.6 factor. So 3 multiplied by 0.6 is equal to 1.8 del O. So overall value of del O for D9 system involving copper, silver and gold for both strong field and weak field ligands is 0.6 del O. D10 system includes elements such as zinc, cadmium and mercury. All the orbitals are filled. So these are the 10 electrons. So 6 electrons will go into dxy, dyz and dxc, and the 4 electrons will go into dx square, y square and dz square. So if you see here, all electrons are 10 electrons are placed in these orbitals. So all the orbitals are completely filled. So for D10 system, 6 multiplied by 0.4 is equal to 2.4 del O for these electrons, and for these the value will be 4 multiplied by 0.4 is equal to 2.4 del O. And again in D10 system the overall value of CFSE is equal to 0, which means these complexes are also least stable. Again zinc, cadmium and mercury, these obtain the value of 0 because the orbitals are already filled, and we know that filled orbitals don't want to make any other bonds because they are already filled. These elements are already stable, so they don't want to form any further complex because they are already stable. So that is why the value for zinc, cadmium and mercury complexes is 0. And if we see here in the examples of coordination chemistry, that the central metal element for zinc, cadmium and mercury, these complexes you will not see so much frequently. So that is the experimental proof that what we are doing here as far as energy calculations are concerned, we are going in a correct path, and this 0 value is expected just like that of D5 system. Now if we summarize the all CFSE values for system like D1 system, the value of CFSE for octahedral geometry is 0.4 del O. For D2 system the value is 0.8, and for D3 system the value is 1.2. As D3 system has value greater as compared to D2 and D1, it means D3 system containing complexes will be more stable as compared to D2 system, and D2 system complexes will be more stable as compared to D1. Now the D4 system such as chromium, molybdenum and tungsten, these have two cases like strong field ligands and weak field ligands. For strong field ligands the value is 1.6, whereas for weak field ligands the value is 0.6. It means D4 system with strong field ligands will make stable complexes as compared to D4 system with weak field ligands. D4 system strong field ligand case will also made complexes more stable as compared to D2 and D1 system. Similarly, D5 system contains two cases, strong field and weak field. In case of strong field, the value is 2.0, which is highest as compared to D4 strong field and weak field, D3, D2 and D1 system. Whereas D5 system with weak field ligands, the overall value is 0. This 0 indicates that D5 system like manganese, technetium and rhenium, these complexes have half filled orbitals. They don't make any complexes, and we don't see their complexes so much often in coordination chemistry because these elements are already stable due to their half filled orbitals, so they don't get into the hassle of making further complexes. Similarly, D6 system contains two cases. Strong field case the value is 2.4, for weak field the value is 0.4 del O. So we have seen that in case of these cases Always the weak field ligands will make less stable complexes as compared to strong field, as we have seen it in D4 system, in D5 system and D6 system. Similarly, in D7 system the trend is following the same, like strong field case will make stable complexes as compared to weak field system. Then D8, D9 and D10. In case of these three systems, there are no such cases like strong field and weak field. The result will be same, either the ligand is strong field and weak field. For D8 system the value is 1.2 dallo, for D9 system value is 0.6 dallo, and for D10 system like for the elements such as zinc, cadmium and mercury, the value is again 0. This 0 is due to that D10 system means that element has already completed its shell. It doesn't need any further electrons to gain the stability or to attain the next noble gas configuration. So that is why D10 system will also not make complexes, and if they somehow try to make complexes, their complexes will be least stable, as the CFSE value for this is 0, just like that of D5. Another trend we have seen here, that if you see here that the energy of D1 system and D6 system for weak field ligands is same. Like for D1 system the value is 0.4 dal O, and for D6 weak field the value is 0.4 dal O. Similarly, the value of CFSE for D2 and D7 weak field ligand case is same, D3 and D8 is same, D4 and D9 is same, and D5 and D10 is same. So this is the overall summary of the CFSE values for octahedral geometry for both strong field and weak field ligands. This was all about today's lecture. I hope you have understood it well. If you have any question, let me know in the comment section. I will respond as soon as possible. In the next lecture, we will calculate CFSE values for tetrahedral geometry. So stay tuned. Okay, thank you. Allah Hafiz.